Okay, so today we're going to talk about the Gaussian software computational chemistry items, and that's related to today's lab, or this week's lab. You're going to get into the lab and you're actually going to put into practice some of these skills that you're learning today, or at least I'm talking about today. And so what is the Gaussian software and what can it do for us? Think about what we did for the particle in a box, those 6 pages of calculus and algebra. That was an attempt to kind of give you an idea of what's going on behind the scenes in Gaussian. So it's taking the wave functions and using the Hamiltonian and solving for the energies of the molecule, moving the geometry of the atoms around and doing it again. And so it's iterative, and it finds the minimum structure of a molecule, and then it looks to see how it vibrates and gives you the vibrational frequencies. So the things we learned in the first part will continue on, like 3n minus 6 vibrations, 3 rotations, 3 translations, and so on. All of that's built into Gaussian. So let's look at the software for a little bit. Your interface to Gaussian, the actual computational engine, is going to be called GaussView. So this software that we have on those laptops in the other lab. And now if you want to bring your own laptop to a lab and get Gaussian on your laptop, we have a site license. You can use it while you're a student here. And so if you just are comfortable working on your own system. Now, we don't have it for Macs. We just have it for PC. Not making any statements. That's just what we have. But so you might want to use the in-house laptops if you have. They're brand new, or they're 1 year old, so they're pretty good. And it's really easy to build molecules. You just, whatever molecule you have in this little window, that's your little active molecule. You click anywhere in here and you can add that molecule. If I have like this methyl group active and I click on this hydrogen, it'll stick a methyl group on that hydrogen. And so you can just build long chains by just clicking, and it's super fast. You can click up here, this where it says carbon tetrahedral. You can click there and you end up with the element, select the element panel, and you can get the whole periodic table. Also, you can choose atom types. So like if you pick carbon, you have a choice of all of these different types of atoms. You have sp, a couple of different sp types, an sp2, sp2 sort of with delocalization, kind of like an aromatic system, and an sp3. So you can build all different kinds of molecules. Once again, we're sort of depending on our Lewis dot structures and Vesper shapes, but we're skipping over the Lewis dot part and just doing right straight to the Vesper shapes of our molecules in 3 dimensions. And this is an initial guess. So Gaussian will then relax the geometry and find the minimum energy of your molecule. Sometimes it's hard to build like ring structures, and so they've made a panel for ring fragments. And so if you click this second little button up here that looks like a benzene ring, you get all of these different rings. If you click this one, benzene is by default, but if you click the button that says benzene, it gives you access to all the other templates. Some of the ones that are difficult to build by hand would be the cyclohexane ones. So here's the chair form, here's the boat form of cyclohexane. Some of the strained rings, like some of these epoxide groups, are kind of hard to build by hand, and so they have these little ring fragments. So don't worry, don't forget about these other kinds of tools that they have. If you're trying to build a really complicated molecule, you definitely want to use these tools. Sometimes you might need to think a little bit out of the box to say, well, I want to make like caffeine, right? And it's got some nitrogens in the ring. Well, none of these, notice this doesn't have nitrogen. Here's a kind of a caffeine-like structure. So you click that, and then you switch the element. You go back up here to this carbon. You switch the element to nitrogen, and then if you click on the atom in that structure with a nitrogen atom, it'll turn it into a nitrogen atom. So you can start with like an all-carbon hydrogen structure, and then you can change the atoms pretty easily just by clicking on them. Enjoy your time. I mean, poke around in GaussView, build some fun molecules. And then there's an R group section. You can click this, and these are a bunch of different functional groups that you can have, like nitro groups and carboxylic acid groups and phosphates and so on. even down here, kind of a base porphyrin ring structure. So once you have your molecule built, and we're building really easy ones this week. I think we're just building like some diatomics so that we can calculate our results. And then later when we do lab results like carbon monoxide, we're going to solve for the bond length, and you can compare them to your Gaussian results. And so the calculations that you have to do this week are very simple, but they're prepping you for the experimental stuff that you're going to do. And then you'll have theoretical and experimental, and you can compare the two. When it comes time to do the calculation, just come up here to the Calculate tab or menu item, click Gaussian Calculation Setup, and you get this panel down here with all of these tabs. And we'll go through most of these tabs here in a sec. So there's two software packages. There's GaussView and then there's Gaussian. And so this is setting up the calculation input file for Gaussian, and it's run automatically from GaussView. So let's skip the job type for now and go to the method tab. So this method tab has several options on it. This is where we pick whether it's a ground or excited state calculation. All of the calculations we're going to do in this class are ground state calculations. It also has a thing called level of theory designation. So this piece right here, these two little boxes, are level of theory. And then this one is labeled basis set. And so you have two parts to a calculation. You've got to tell it what level of theory and what basis set to use. And we'll explain what those mean in a second. Then you can calculate ions. Okay, so you can have charged species. And then the spin here is important. This is essentially the number of unpaired electrons plus 1. Okay. So whatever this multiplicity is the number of unpaired electrons plus 1 will give you that. And so if you have 0 unpaired electrons, most of our molecules have an even number of electrons, everything's paired up, and so it has a multiplicity of 0, it has a spin of 0, and so a multiplicity of 1. So we have 0 unpaired electrons, and 0 plus 1 is 1, so we have that multiplicity. And so let's talk about this selection of a theoretical model. Think about if you had like the pChem model kit, and you made a molecule, and you were going to talk about the bond length, and you measured the bond length with a ruler. So it's like 1.5, 2 centimeters long, and then someone else used a different model kit from a different manufacturer, and they built the same molecule, and they measured their bond length as a bigger kit, so their bond length was 4.5 centimeters long. You realize how stupid it would be for you to argue over who was right? Because you used one model kit and the other person used a different model kit. Same thing for the calculations. Whatever level of theory and basis set you use is going to give you a set of bond lengths, a certain geometry. And so you can't compare that model chemistry result to some other model chemistry result. If you have different model kits, you're going to have different answers. Now, they may not be that much different. They may be pretty close. And sometimes you want to do that. Calculate it with progressively more expensive models, meaning longer calculations. And when the bond lengths and angles stop changing, why go any further? Why spend more computational time? So the real cheap, inexpensive models that are done in a few seconds will give you a nice guess, but it's probably not going to be very accurate. Pretty soon, though, as your calculation goes to hours or so, then you're going to start getting some more accurate bond lengths and angles. And so, but anyway, whenever you're calculating things like delta H of reaction or delta G of reaction, you want to use the same model chemistry for the products and the reactants, because you're going to take differences. Also, the selection of a basis set. This is the math, or let's say the functions that we give to the electrons in the molecule and the nuclei, but mostly the electrons. And the more freedom the electrons have, the more realistic the model, because the electrons don't know math. They haven't had calculus. They don't know they're supposed to stay in this p orbital function. Okay, we've used those spherical harmonics to model the hydrogenic orbitals. and the electron knows nothing about that. Okay, so the electron has total freedom. It's looking at a molecule with all of these nuclei, and our mathematical models with p and d orbitals get us pretty close to the true answers. Okay, but they're not. I guess they're our mathematical approximations. They're not known by the molecule or the electron. The electron can do whatever it does. I mean, you walk across carpet in a certain pair of shoes and you pull electrons right off the carpet. They're not supposed to do that. Right? They weren't told they're supposed to stay on that atom. Okay, electrons are going to do whatever they do, and so the more freedom we give them, then the more accurate the results. And then we'll get into graphical models, what we do after we've done with the calculation, what can we look at around the molecule, which includes molecular orbitals, electron densities. This is where those pictures come from that I've been showing you in the class notes, the red and blue orbitals. So this is the main approximation that allows us to calculate the electronic structure of a molecule, is that the nuclei are so massive that in terms of the electrons, it's almost like the nuclei are not moving. This is what we call separation of variables. And think about you, and have you ever been in a cloud of gnats? You know, and you wave your hands and you move, and it doesn't seem to bother the gnats because you're so big and slow. Like you're waving your hand at them, and that hand is moving like a glacier to the gnats. They don't even care. They don't even know that it's moving. The same with the electrons and the nuclei. So we can take advantage of this, and we can fix the nuclei in space and calculate the orbitals of the electrons. And then we can move the nuclei and calculate the next set of orbitals. And so this separation of variables is a really helpful thing. It's the Born-Oppenheimer approximation. And so the gnats or the electrons cannot even tell that you or the nucleus are moving. So we might as well fix the nuclei, calculate the electron cloud, then move the nuclei, calculate the electron cloud, and see if we went down in energy. If we did, keep going in that direction. Eventually, we go back up, and we found the minimum energy, so we know the locations, the bond lengths, the angles of the nuclei. So this is an iterative process. It's kind of like your old, you learned guess and check, right? We guess and check our results. We guess on the location of the nuclei, calculate the electron cloud, check to see if that energy is the minimum. And once it is, we stop. So this iteration result is put out in our output file, and that's why you never print an output file from Gaussian, because 90% of it is just this iteration stuff. So it's useless information for the most part. You want that last calculation that has all of the bond lengths and angles of your optimized geometry. So let's think about this electronic structure. It's the molecular Hamiltonian. So you guys know the Hamiltonian. It's the minus h bar squared over 2m times the second derivative of the wave function, and that's it. But it gets a little more complicated when you have a potential energy function. For the particle in a box, ours was 0. For a molecule, you have Coulombic attraction and repulsion. You have positive nuclei that hate each other, and nuclei and electrons that like each other, and electrons that hate each other. So these are 5 terms in the molecular Hamiltonian. The T's represent the kinetic energy, and the V's represent the potential energy. And I'll go ahead. So this, so you can see it. So these two right here are the kinetic energy parts. And I just write Ke for kinetic energy, and then the V's are the potential energy. Now, how do we calculate the kinetic energy of the wave function? We take the second derivative of it. Okay, and so these first 2 pieces ought to look somewhat familiar. Here for the electron piece, it's kind of like our electron in a box. We have h bar over 2m in the mass of the electron, and we have the sum for each electron, the second derivative of that electron's wave function. So this upside down delta is a shorthand for the second derivative with respect to all coordinates. So x, y, and z, or r, theta, phi, whatever. There's also the kinetic energy of the nuclei. And because the nuclei have different masses, potentially, they're inside the sum. And so for each nucleus, we go through, for that nucleus mass and its wave function, we take the second derivative. So these are the two kinetic energy terms. And so you can see alpha and beta are nuclei, I and J are electrons, Ma is that isotopic mass for the nucleus, Me is the electron mass, and these upside down deltas, we call them del, not delta, just del. So del squared represents that second derivative with respect to all the different coordinates. Now these are partial derivatives, so if you haven't had Cal 3, this is taking, let's do xyz since we're familiar with that. This is taking the derivative with respect to x, treating y and z as if they're constants. Okay, and then the next one, on the same wave function, we take the derivative with respect to y, treating x and z as if they're constants. And so those are called partial derivatives, and that's why this little d looks funny. You see, it's kind of like a regular d, but in a windstorm. Okay, so that's the kinetic energy pieces. Well, we have potential energy pieces. So we have Coulombic attraction. So this is the nucleus repulsion. So it's a positive term because it's repulsive. It's the charge on nucleus alpha, the charge on nucleus beta, and then this is the little, I should say Z's are the number of protons in each. So the number of charges in alpha, the number of charges in beta, and then this E is the elementary charge for a positive charge. So essentially we're saying, it's all of the positive charges times each other. And then this 4 pi epsilon naught, that's the permittivity of the vacuum. That's how charge kind of decays through space. Okay. And then this is the distance between the two nuclei. So that's easy to calculate in Gaussian. We give them, like with our little clicking of the atoms in our building window, we're giving them the nuclei positions. So Gaussian knows the coordinates for all of our nuclei, and it can easily calculate the distance between every pair. So this is pretty straightforward, incredibly tedious. There's no way I'd make you do this by hand. It's wonderful that Gaussian does this for us. Okay. Then we have the nuclear electron attraction. So we have on nucleus alpha, we have the number of protons in alpha. We have a minus sign because it's attractive. So it lowers our energy as they get closer. And so for every nucleus alpha, we loop through all of the electrons. And so we start with nucleus 1 and we go through every electron. How is every electron attracted to this nucleus? Then we go to the next nucleus. How is every electron attracted to that one? So again, very tedious, as you might imagine, going through every one of the nuclei and calculating every electron. Also gets pretty involved when you start adding transition metals. You have so many more electrons. And then lastly, we come to this, we have these pairwise differences, and then we have this last piece called electron correlation. This is the electron-electron repulsion. And this is where we have the trouble, is trying to calculate the position of the electron, because the electron is being treated by a wave. And so we only have probabilities of where the electrons are. We don't have the position of the electron. Now we can treat it maybe at its most probable spot, but the other electron may not be at its most probable spot. And so how do we calculate this term? We don't know. This problem's never been solved. So this Rij term is a real problem because our electrons are not discrete particles. They don't behave that way. They behave as waves. So they really have kind of a dance that they do that we cannot describe. We have never solved that problem. We've solved all of the single electron problems. So we can do hydrogen. We can do helium plus. We could even do uranium 91 plus. It only has one electron. Okay. But if you get to 2 electrons, we can't solve the Hamiltonian. And so that's why we have all these different levels of theory in this calculation package. Okay. It's called electron correlation, and that's the problem that we have that we cannot solve. There are no analytical solutions. You will definitely win the Nobel Prize if you solve that problem. Okay, you're going to take Cal 3 and a whole bunch of other math. We've come a long way since the particle in a box. So can you understand now why I emphasize the particle in a box if we're going to do it by hand? We go through that one absolutely analytically. Okay, but then when we get to real molecules, we need a computer's help. So this is, because of this electron correlation, we need to select a model chemistry. And so we must do some sort of approximation that takes into account that Hamiltonian electron correlation piece. And here are different model chemistries. So, Samantha, can I get you to close the door? And so we have different examples. We have molecular mechanics, we have semi-empirical, ab initio methods, and configuration interaction, and the density functional theory. So these are some, I've underlined some of the ones that I use quite often. UFF stands for Universal Force Field, AM1 is Austin Method 1, HF is Hartree-Fock, and then B3LYP is a density functional theory. So we'll go through all of these different types of calculations. So these are different model kits that we can use in the computational package. And if we're doing delta H of reaction, we would want to use the same one for the reactants and the products, as I said before. Molecular mechanics is the fastest, okay? Because it ignores all the electrons. So one way to get rid of electron correlation is just ignore the fact that there are electrons. Now you say, how can that possibly be useful? Well, what it has done is it said, okay, there's a particular function here. This is the Lennard-Jones 612 potential. So this Lennard-Jones, that's the name of this potential here, this equation. And it's the 612 potential because of the exponents here. And so this, has an attractive term here. This negative term is attractive, right? Because it reduces the energy. And it falls off as 1 over r to the 6th power. But then there's a repulsive term here. That falls off as 1 over r to the 12th power. So when the nuclei get too close, they repel each other. And so this is 1 over r to the 12th. And this is 1 over r to the 6th. And somewhere in the middle, they're going to be a minimum. And that minimum here is the energy of that interaction. So it has a particular bond length it likes, and it has a particular energy associated with that bond length. Now get your mind away from covalent bonds. This is every pair. So this could even be hydrogens on opposite ends of the molecule. Now they'll do maybe some speed up things and say if a element is more than X, angstroms away, don't even calculate the potential because it's 0, right? But brute force, it would calculate every energy from every atom to every other atom in the molecule. And it would say that's the energy of the molecule. It adds up all those energies. And then it can move the elements and see if the energy dropped or went up. And so it can find a minimum energy using this. And because you just have the number of nuclei, it's a very fast calculation. Okay. So it's really good for large systems like proteins and polymers. And you select it by choosing on that method tab. You choose mechanics here in this drop down, and you have 3 options: universal force field, Drying, and amber. I have really no reason to suggest one over the other. If you're doing molecular mechanics, you may want to look for papers that calculate similar things to what you're interested in. And you would want to repeat those calculations in the literature first to see if you got the same answer. And that tells you know how to do the calculation. And then you start calculating your unknowns. Okay. Semi-empirical methods will speed things up by eliminating all the core electrons. Okay, so let's look at carbon. Carbon has 6 protons in the nucleus. It comes in with 6 electrons, but there's only 4 valence electrons. So we could reduce the problem quite a bit by eliminating 2 of those 6 electrons, the core electrons. We don't get too much speed up for carbon, but look at chlorine. Chlorine comes in with 17 electrons, okay? but there's 7 valence electrons. So now we're able to eliminate 10 out of 17. So semi-empirical really speeds things up by eliminating the core electrons. And so it's using the full Hamiltonian on all the valence electrons, but still ignoring that electron correlation term. Now, you can't just get rid of the core electrons, especially on chlorine, because the nucleus has 17 protons. So the nucleus is charged 17, and those outer 7 electrons are going to behave very differently if they're attracted to something charged 17 versus something that's shielded by the core electrons. So they'll take that nuclear charge of 17 and they'll reduce it to account for the electrons that they deleted. Okay, so instead of making the nucleus have a charge of 17, it might be 8.5. Okay, so there's some incomplete shielding of those of the nuclei by the core electrons, and they will look at experimental data. That's the semi-empirical part. The empirical is experimental, and they will adjust those core potentials to match the properties of chlorine and the properties of bromine and carbon and so on. So they'll take into account experimental data, they'll adjust those core potentials and get rid of the core electrons, and that's how they speed things up. They do really well for atoms and atom types that don't break the rules. So what is an atom type that breaks the rules? Think about cyclopropane. Okay. So you have a cyclic molecule, 3 carbons, CH2, CH2, and CH2. So each of those carbons has 4 electron domains. What are the bond angles around something that has 4 electron domains? It was just on the last test. 109.5, exactly. The bond angle in this molecule on the inside is 60 degrees. So if you're modeling this molecule with a semi-empirical method and you're using sp3 type carbon, that's going to be a really strained ring. In fact, it may even fail for this molecule, okay, because it's not, those core potentials were adjusted to match the data on normal molecules, and this is not necessarily a normal molecule. Okay, then we get into the more rigorous, I would say expensive calculations. Whenever we talk about expense, we mean the length of time it takes for them to finish. All of those earlier ones, molecular mechanics and semi-empirical, if it's just a normal molecule, benzene or something like that, I mean, it's done in a few seconds, 20 seconds maybe. Hartree-Fock and DFT, they take quite a bit longer. So there are different theories for estimating the electron correlation, and Hartree-Fock theory just ignores it altogether, but it does calculate the repulsion term and the attraction term for every electron. Then there's some corrections that they can do to the wave functions, and it's called perturbation theory. And so this, because it was a sort of a historical adaptation of the wave functions to get to be more accurate results, they've included that in Gaussian, but they're really costly and they don't give you as good a results. So it's, I would say, seldom used because it's really expensive time-wise, and there are other methods that are better. So why not use the better methods? Coupled cluster methods are interesting. They look at the refinements to the electrons by exciting electrons into the unoccupied orbitals. And so they look at different configurations and how they interact to improve the wave functions, and a better wave function will give you better results. But they're pretty costly too. I think density functional methods are probably the best workaround in terms of accuracy versus cost. So that's why they're so popular. So to select a density functional theory on the method row, you pick DFT, and then you have to tell it what type or flavor of DFT. You have all of these choices over here, and so it's kind of daunting. You have no idea why to pick which one. So this B3LYP has sort of been the go-to standard for years, but now I think things are shifting over to this APFD. So those would be the two that I would consider using. I think in our class, in our labs, we have the B3LYP spelled out in the lab handout, but I'm starting to shift things over to APFD. So that's the level of theory that we're using. Now we need to talk about how much freedom the electrons have in our basis set or our wave function. And so the requirement is a level of theory and a basis set. So these are the two ones that I've talked about. Let's go now to the basis set. So one way to approximate this electron correlation term is, again, through these effective nuclei charges. So we can reduce the charge on the nucleus in that potential term by this shielding. So this gnat is being shielded by all of these other gnats, and the charge on this nucleus, Z, is reduced to account for the shielding of all of those other electrons. So let's talk about basis sets. This first one, the STO3G, Slater-type orbitals, these are the minimum basis sets for the atomic orbitals, and these are the ones that you're familiar with. They're not very accurate, but at least they are the ones that we learned in freshman chemistry. The S orbital, the P orbital, the D orbital, and the F orbital. And that's pretty much as high as it goes, okay? And it puts only as many orbitals as you need for the ground state atoms. Okay. And so you could think of the electron configuration of carbon. You have 1s2, 2s2, 2p2. It's going to put those orbitals on. It's not going to put 3p or 3d orbitals on carbon. Okay. But we can in some of these higher basis sets. Then we get into these different primitive Gaussians and so on. It gets pretty confusing. And so the reason this program is called Gaussian is because it's not using the hydrogenic orbital, the radial distribution function. So this was the analytical solution for hydrogen. Let me just write that. So for hydrogen, the analytical solution, the radial distribution function was e to the minus r, with some constants in the top and constants out front to normalize it and everything. But the main function was an e to the x type function. It was e to the minus r. But a Gaussian function is e to the minus r squared. And the reason we like Gaussian functions is because there are instantaneous analytical integrals to those. So we can just look them up. We don't have to do numerical integration. We can just look up the integrals for Gaussian functions, and things are very fast. So if we could approximate this analytical solution with a bunch of Gaussians, so we take a broad Gaussian here, and then we bring in a couple of smaller ones that are sharper, then this result, notice, is a little taller in the middle and still kind of has the right decay out here. And so we're trying to approximate this blue curve using a whole bunch of Gaussians. And that's what Gaussian software is doing. They named it after their function that they're using to approximate the radial drop-off of the electron cloud. And so one way to make it more accurate is to include more Gaussians in that approximation. And so that's what we have right here, is all of these different basis sets are all different ways to add orbitals onto our atoms so that the electron has more freedom. And with more freedom comes more cost. Okay, so it's going to take longer to calculate. Then, as far as around the nucleus, we have things like p orbitals and d orbitals. Those are called angular momentum functions or polarization functions. And so we can add that to all the heavy atoms, which means all the atoms other than hydrogen, or we can add them to those elements and hydrogen. It helps to they built a program to where you can split off hydrogen and treat all the elements other than hydrogen a certain way, and then treat hydrogen its own way. And so the first little box in all of these cases is for the heavy elements, the non-hydrogen elements, and then the second box is for the hydrogen elements. And so you can put d orbitals on a carbon atom when it's pretty far away from the 3d orbitals energetically. But this allows the software to use, say, 10% of a d orbital. It doesn't have to put an electron totally in a d orbital. It can mix all of those functions in certain percentages. And so if it doesn't need that d orbital, it won't use it. It'll be like 0.0001 times that d orbital. But if it does need it because of the complication, maybe that cyclopropane molecule where you need those angles of 60 degrees, well, d orbitals and f orbitals might help in that situation and give you a better energy. Because again, the electron's going to be attracted to that other carbon, and it's not going to care that it's at 60 degrees. The electron's going to do what it does. We call these higher angular momentum or polarization functions. The more freedom you give the electron, the better the result. But it does take a long time. And sometimes you might have anions where you want a big electron cloud because the electrons repel each other, and so you want to add diffuse functions. Again, the first plus would be for non-hydrogen atoms. If you include both pluses, you're getting all the atoms. There's really no way to put diffuse functions on hydrogens only because that doesn't really make sense. You would do all the heavy atoms first, and then if you want to check the result with hydrogen, you could put them on hydrogen 2. So transition states and anions, you might want to use diffuse functions. For like a monster basis set for good energies, this would be a monster basis set. We're putting d and f orbitals on the heavy atoms and p and d orbitals on our hydrogens. There's a hydrogen with a d orbital. Probably using 1% of that d orbital if necessary. So here's this little selection guide. If you have a huge system, you want to use molecular mechanics or semi-empirical methods. The latest suggestion, because computers have gotten faster, is this basis set suggested by Forsman and Fritsch in their 3rd edition of Electronic Structure Methods. So once we have the model chemistries and level of theory with the basis set, we need to build our job. So let's look at that next. So our job types, the most common is going to be this optimization and frequency calculation. You can tell it here to calculate the Raman intensities, and so I always say yes to that. You can even do things like NMR simulations and UV vis spectra too. There's a title tab. You can type anything in there. I would avoid using special characters though, because some of the search terms that you want to use later will be screwed up by that. And then let's talk about computational times. This is on TATB, an explosive molecule. I started using this program in '92, and it was taking me about 20 hours to calculate this on my PC. I had a smoking fast PC, 486 megahertz. Okay. And so 20 hours, right? Then when I got here, I started working on this was before I got here. 98W, I think, is when I first got here. It was taking 24 minutes. So from 20 hours to 24 minutes. And then Gaussian 03, less than 5 minutes. I need to calculate it on Gaussian 16 to see how it's sped up. But if I also had a grad student that on a computer here, the Pentium 4 3 gigahertz machine, had a calculation take 2 weeks. And so if I look at this time function going back in time, how long would that take the 1967 polyatom program? 1,500 years. That's so weird to me. It's like a Doctor Who thing. You're in 1967 and you want to calculate this molecule and it's impossible. It'll take 1,500 years. Just wait a few decades and you can do it in 2 weeks. That's bizarre. That shows you how fast PCs and computation is sped up. Things that were impossible in the past are now possible. And things you can do on a laptop. It's just crazy. They don't have a Gaussian for your phone yet, but your phone is way more powerful than that polyatom 1967 supercomputer, right? And so we'll probably finish up with this. This is what Gaussian's doing with the optimization and frequency calculation. You give it the nuclear coordinates by building the molecule. It calculates the energy and the slope with respect to those coordinates, and it determines whether it's at a minimum or not. If it's not at a minimum, it changes the geometry and starts over. And so this loop here is what produces most of the output, and that's why your output file is full of so much stuff you're not interested in. And then eventually you reach a criterion that says it's converged. It's at the bottom of the well. And so then it starts another calculation, a frequency calculation, that calculates the vibrational frequencies. Now, if you happen to be in a harmonic oscillator, the vibrational frequency is positive because it's above the minimum. But if you're at the top of a hill, let's say you're at a transition state and you didn't know it because you've got a methyl group or something that can rotate, then that vibrational frequency is below the critical point, and it shows up as a negative frequency, less than 0. And so those negative frequencies are, because this is a negative result of, it's like x squared, okay, it's an imaginary number, and so that's why they're called imaginary frequencies, also negative frequencies. And so if we have some of those, we need to reduce the symmetry of the molecule and start over with our geometry optimization. And then if we get all the way down and we have no negative frequencies, then we're at least a local minimum. We may be at the global minimum. And so we have that optimized geometry and energy data. And then with that, we can calculate the spectra, molecular orbitals, the electron cloud, electrostatic potential energy maps. I've got 1 minute, so let me just talk about those. We've seen these pictures. That's where those pictures come from. This is the picture of the electron cloud, the total electron density around the molecule. Okay. We could walk around on top of that electron cloud with a positive charge in our hand, okay, calculation-wise in our computer, and see where the positive charges and negative charges are, and that's what we call an electrostatic potential map, an ESP map. And this says the electron cloud does not, this is benzene, does not quite cover the hydrogens. And so when I'm on this end, I see a hydrogen. Guess what I'm going to look for if I'm a nucleophile? Yeah. And if I'm over the top where I have all of those pz orbitals interacting, I've got a lot of electron density in the ring. Guess where I'm going to go if I'm an electrophile? And so this software can now predict the reactivity of the molecule, where we're going to have nucleophilic attack, where we're going to have electrophilic attack, elimination, all of those different things. That's why I always wish we could teach pchem right after Chem 2 before you go into organic, because then all of the reactivity of those reactions would make sense to you. Okay, but it'd be kind of a heavy lift. I think the drop rate would be a little high, but still, you know, it would be a fantastic thing. I've always wanted to do that, but they won't let me experiment on a whole class of students. We can look at pKa's. We can calculate the proton, you know, removal ability and so on using this software. And so there's a lot of information we can get once we have that geometric optimization. We can get bond lengths and angles and potential energy surfaces. And so in the notes, you can see how good the bond distances are, the vibrational frequencies, and so on. So I will not see you on Wednesday, okay? And we'll see you on Friday, hopefully. Take care.